Welcome, curious minds, to another deep dive. Today, we're going to explore some really fascinating materials. I mean, imagine these intricate cage-like crystals, but down at the atomic level.
Yeah, they're like tiny, perfectly constructed molecular puzzles.
Almost like prisons for atoms.
You could say that.
Yeah.
And what's truly captivating about them is their potential. They might seem like just a scientific curiosity, but honestly, they hold profound implications for future tech.
Future tech like what, specifically?
Well, think next-generation batteries, for starters. Also, things like thermoelectrics, that's converting heat directly into electricity, and even superconductors, materials that conduct electricity with zero resistance.
Wow, okay, that's quite a range. So for this deep dive, what's our main focus?
We're zeroing in on a specific type 2 germanium clathrates.
Right.
We want to explore how really understanding their atomic scale structures and how things move around inside them can lead us to much better energy storage.
So we're going from these tiny, tiny cages.
Exactly, from those microscopic structures to potentially, what powers your phone, your laptop, maybe even your electric car down the road.
Okay, let's unpack this intricate world then. So just to start, what exactly are these Clathrates? You pronounced it Clathrates, right?
That's right, clathrates. At their core, they're unique structures, often called host-guest structures.
Host-guest.
Yeah, think of a crystal lattice, the host, forming a kind of atomic cage. And inside these cages, you have individual atoms, the guests, that are essentially trapped.
Okay, and for this deep dive, the host is germanium, making the cages.
Precisely. Germanium forms the framework.
And the guests trapped inside are sodium atoms.
Exactly. The specific material we're really digging into is called sodium-filled type 2 germanium clathrate with variable sodium content.
Okay, variable sodium content. That sounds important.
It is. It's crucial. It's often represented by a delta symbol, like a little triangle in the formula. It means we can actually control how much sodium is inside.
And why would you want to do that?
Because by adjusting that sodium level, we can fine-tune the material's properties. Things like its electrical conductivity or how easily ions, the sodium ions in this case, can move through it.
Ah, so it's like having a dial you can turn to get the performance you want.
Sort of, yeah. It gives us a powerful way to design materials for specific jobs, like batteries.
Now, you mentioned these cages. Are they all the same size and shape?
No, actually, the structure has two distinct types of cages made of germanium.
Okay.
You have the smaller ones, called germanium-20 cages. They're dodecahedra, which means they have 12 sides. Think of tiny molecular soccer balls.
Molecular soccer balls, I like that. And the other type?
Those are the larger germanium-28 cages. These are hexadecahedra.
Oh, say that again.
Hexadecahedra.
Okay, hexadecahedra.
Got it. Yeah, it's a mouthful. They have 20 sides, so they're bigger, more complex polyhedra.
And how do these different cages fit together?
They arrange themselves in a really intricate, perfectly ordered way at the atomic scale. You could almost picture it like a molecular honeycomb. It's a very precise crystal structure.
It's incredible to think about that level of organization. Now, you mentioned batteries, but also thermoelectrics and superconductors.
Yeah.
What makes these clathrates promising for those other areas, too?
Well, take thermoelectrics. That cage structure is really good at scattering the vibrations that carry heat, but it still lets electrons move through pretty easily.
So it blocks heat flow, but allows electricity flow.
Yeah, exactly, which is just what you want for converting waste heat into useful electricity efficiently.
Makes sense. And superconductors.
Certain types of clathrates show superconductivity, zero electrical resistance, though usually at very low temperatures. But yeah, it's another fascinating property.
But for today, we're really honing in on the battery potential.
Right. That's where these materials, particularly the germanium-sodium ones, seem to really shine.
So what is it about their structure that makes them so good for batteries?
It really comes down to their unique ability to store ions, the sodium ions, and let them move in and out efficiently.
Okay.
That efficient movement is key for charging and discharging a battery. And because of the structure, they could potentially lead to batteries that are smaller, lighter, and last a whole lot longer.
That's the dream for everything from phones to EVs.
Absolutely.
And there's a stability aspect too, right? Something with volume change.
Yes. And this is hugely important for batteries. When you take all the sodium out, going from a fully sodium-filled type 2 germanium clathrate to what's called a guest-free type 2 germanium clathrate, the volume only changes by about 5.45%.
5.45%. Is that small?
It's remarkably small. Compare that to other materials being looked at for sodium-ion batteries.
Like what?
Well, things like amorphous sodium silicide can swell by 230%. Amorphous sodium antimonide, maybe 300 to 400%. Sodium phosphide, 330%. Sodium stannate, 420%. Massive changes.
Wow. Okay, so compared to those, 5.45% is practically nothing.
Exactly. And that tiny volume change means the material is much more stable when you charge and discharge it over and over again.
It doesn't break itself apart from expanding and contracting so much.
Precisely. That leads to much better cycling stability, meaning a longer-lasting battery. It's a massive advantage.
Okay, so we know what they are and why they're exciting for batteries. How do scientists actually make these things? It sounds like building with atoms.
It kind of is. The process usually starts with a specific precursor material. In this case, it's called tetrasodium tetragermanide.
Tetrasodium tetragermanide. Okay.
Right. It's a type of compound known as a Zintl phase. What's important is that it basically provides the right starting ratio of sodium and germanium atoms, perfectly balanced to form the clathrate later on.
So it's like having the right ingredients pre-mixed. What's the next step to turn it into the clathrate cages?
The critical step is called desodiation.
Desodiation, removing sodium.
Exactly. It's the controlled removal of some of those sodium atoms from the precursor.
And that removal triggers the cage formation.
Yes, it's quite a transformation. You used the prison analogy earlier, but maybe a better one here is like a caterpillar turning into a butterfly.
How so?
Well, as you carefully pull out the sodium atoms, the remaining germanium atoms don't just sit there. They rearrange themselves, and that rearrangement causes them to snap into place, forming those characteristic germanium-20 and germanium-28 cages.
That's a great visual. How do they actually do this delicate sodium removal in the lab?
Typically, they heat the tetrasodium tetragermanide precursor, but under very carefully controlled conditions, specifically controlling the sodium vapor pressure around it.
Ah, so they control the atmosphere it's heated in.
Right. By adjusting the temperature and the composition of that sodium vapor, they can precisely control how much sodium leaves the structure.
And that lets them control the final sodium content in the clathrate, the variable part we talked about.
Exactly. It allows for that fine-tuning.
You mentioned temperature is key. Does changing the temperature give you different results?
Oh, absolutely. Temperature is a major factor determining the final product.
Like how?
The research shows clear windows. If you heat it to around 300 degrees Celsius, you can get various forms of the target material, the type 2 germanium clathrate. That includes everything from nearly empty cages, like nearly guest-free sodium germanium type 2 clathrate, all the way up to nearly full ones, like nearly fully sodium-filled type 2 germanium clathrate.
Okay, so 300 Celsius is the sweet spot for clathrates.
No.
What if you go hotter?
If you increase the temperature to, say, 350 degrees Celsius, you get a completely different material, something called non-stoichiometric sodium germanium hexagonal phase.
Not the clathrate structure anymore.
Nope. And if you go even higher, to 400 degrees Celsius, you basically just end up with alpha germanium, which is the standard diamond-like structure of germanium.
Wow. That's amazing how sensitive it is. A difference of 50 degrees gives you a totally different atomic arrangement.
It really highlights how precise the synthesis conditions need to be.
So once they make these clathrates, how do scientists actually peek inside and see what the atoms are doing? Especially the movement, which seems so critical.
Yeah, watching atoms move is tricky. This is where computational modeling becomes incredibly powerful. They use specialized software tools.
Like simulations.
Exactly. Think of them as partly a virtual microscope and partly an atomic GPS.
Okay, tell me about the virtual microscope part first.
That's mainly a technique called density functional theory, or DFT. DFT is amazing. It lets researchers computationally zoom in right down to the level of individual atoms and electrons.
What does it tell them?
It helps them understand how the atoms are arranged, how they bond to each other, how they interact. They can basically simulate the material's properties and behavior inside a computer, predicting how it will act without needing to run a physical experiment every single time.
So it helps understand the static picture, the structure. What about the movement? The atomic GPS.
Right. For tracking movement, they use methods like nudged elastic band calculations, often just called NEB.
Nudged elastic band.
Okay. NEB is designed to find the most likely path, the lowest energy path that an atom will take when it moves from one place to another within the crystal.
So it maps out the easiest rights for the atom.
Essentially, yes. It figures out the energy barriers involved in moving along different possible paths. So it really does act like a GPS, showing the most energy-efficient road for an atom to travel.
So these simulations, DFT and NEB, were used in this research to understand how sodium gets out of that precursor, tetrasodium tetragermanide, during desodiation.
Yes, that was a key objective, understanding that escape mechanism.
And what do they find? How does the sodium actually leave?
The simulations showed two main ways, two primary migration pathways for a sodium atom, or technically, for the vacancy left by a sodium atom to move within the precursor structure, specifically in a slightly sodium-deficient version.
Okay, two paths. Was one easier than the other?
Oh, definitely. Path 1 was described as being like trying to push through a really crowded doorway.
Blocked, basically.
Pretty much. It involved moving from one specific type of site, called a 2A site, to another 2A site, but there was another sodium atom directly in the way. This resulted in a really high energy barrier, 1.07 electron volts. That's quite a bit of energy needed to make that hop.
Okay, so path 1 is the difficult route. What about path 2?
Path 2 was much, much smoother, like an open door or an express lane.
Nice.
This path went from a 2A site to a different type, a 2B site. Critically, there were no other atoms blocking the way.
So the energy barrier was lower.
Significantly lower, only 0.37 electron volts.
Wow, 1.07 versus 0.37. That's a huge difference.
It is. And this low energy barrier for path 2 helps explain why that precursor material, tetrasodium tetragermanide, can actually be dissociated relatively easily under the right conditions to form the Clathrate structure, or that hexagonal phase we mentioned earlier. The easy exit path is available.
So knowing these specific energy barriers isn't just academic, it tells you why the process works the way it does.
Exactly. It gives you mechanistic insight. If you understand the pathways and their energy costs, you can start thinking about how to perhaps favor the easier path even more, maybe by subtly changing the precursor composition or the process conditions. It provides a roadmap for optimization.
Right, so that covers how sodium gets out of the precursor. But what about once the clathrate is formed? How does sodium move inside the sodium-filled type 2 germanium clathrate itself? What's life like for a sodium atom in there?
Well, life inside the Clathrate cages is also quite dynamic. And this is where things get really interesting, almost like a microscopic social network.
A social network for atoms. How does that work?
Well, the simulation showed, first off, that sodium atoms have a preference. Energetically, they'd rather sit in the center of those smaller germanium-20 cages, the molecular soccer balls.
Okay, that's their preferred home base.
Kind of.
Yeah.
But their movement, their ability to migrate from one cage to another, is strongly influenced by the presence of other sodium atoms nearby their neighbors.
So the neighbors can affect how easy it is to move?
Absolutely. Sometimes they help, sometimes they hinder. It depends on the specific path and how crowded the neighborhood is.
Okay, give me an example of hindering, like atomic traffic jams.
Pretty much. A good example is when a sodium atom tries to move between two of the larger germanium-28 cages. These cages share a hexagonal face, like a window between them.
Right.
Now, if the clathrate has a lot of sodium in it, like the nearly fully sodium-filled type 2 germanium clathrate, the energy barrier to hop through that hexagonal window is relatively high, about 1.8 electron volts.
Okay.
But if you have less sodium overall, the barrier for that same hop might be lower, maybe around 1.3 electron volts.
Why the difference?
Because when it's crowded, the sodium atoms sitting in the neighboring germanium-20 cages actually restrict the hexagonal window from expanding slightly, which it needs to do to let the migrating sodium pass through. They effectively block the expansion.
More neighbors means it's harder to squeeze through the window.
Got it.
But you said they can also help sometimes.
Yes, they can. It's fascinating. Consider a different path. Moving between a large germanium-28 cage and a small germanium-20 cage. These share a pentagonal face, a 5-sided window.
Okay.
Normally, the barrier for this hop might be quite high, perhaps around 4.0 electron volts in a structure with just one sodium atom. But if you have another sodium atom sitting as a neighbor nearby, like in a sodium-filled type 2 germanium clathrate with 2 sodium atoms, that barrier can actually decrease slightly, maybe to 3.85 electron volts.
So the neighbor makes it easier to move. How?
The simulation suggests the neighboring sodium subtly interacts with the germanium framework. It helps to slightly elongate one specific germanium bond that's part of that pentagonal window.
So it kind of pries the window open a tiny bit.
That's a good way to put it. It facilitates the opening, making it just a little easier for the migrating sodium to pass through.
That's really subtle interaction. Were there other ways sodium moves around that the simulations found?
Yes, a couple of other important ones. They found a different mechanism, called a bond-breaking mechanism, for sodium to get out of the small germanium-20 cages, especially when the clathrate is sodium-rich, like nearly fully sodium-filled type 2 germanium clathrate.
Bond breaking, that sounds energetic.
You'd think so, but the barrier for this pathway was actually lower than some others, around 0.75 electron volts.
Interesting.
And another one they looked at was sodium moving out of a germanium-20 cage that was near the surface of the material. They modeled this as a thin slab. That also seemed to involve bond breaking and had a relatively low barrier, too, about 1.22 electron volts. This is relevant for getting sodium in and out of the material overall.
Okay, so we have all these different pathways, different energy costs, neighbors helping or hindering. What's the big picture takeaway for us? Why does knowing all this microscopic detail matter for making better batteries?
It matters immensely because understanding these varied energy costs for sodium movement, how easily it can hop between different types of cages, how neighbors affect it, how it gets in and out near the surface that's fundamental to the battery's performance.
How so?
Well, how quickly you can charge or discharge the battery depends directly on how fast those sodium ions can move through the material. The lower the energy barriers for the dominant pathways, the faster the ions can move and the better the power performance of the battery.
And the stability, the lifespan.
That too. Understanding the mechanisms helps design materials where the movement doesn't cause stress or degradation over time. So these atomic level details translate directly into practical metrics like charging speed, power density, and how many times you can cycle the battery before it wears out.
So it sounds like this simulation work isn't just about observing what happens. It's more like getting a blueprint or even a recipe book for building better clathrates.
That's a perfect analogy. It really acts as a molecular toolkit for scientists.
Mhm.
Having this detailed data allows them to move beyond just trial and error synthesis.
They can actually design materials with specific goals in mind.
Exactly. They can aim for specific properties, like designing a clathrate structure that deliberately has faster pathways for ion transport or lower energy barriers for the sodium to move in and out.
What kind of design strategies does this enable? What can they tweak?
Well, several things. They can computationally explore optimizing the actual size and shape of the cages. They can look at how precisely managing the distribution of sodium atoms within the different cage types affects overall transport.
So not just how much sodium, but where it sits.
Right. And they can even go further and explore using different guest atoms entirely, maybe potassium instead of sodium, or even lithium, to see if that creates new types of clathrates with even better battery characteristics.
So this atom-by-atom understanding really opens the door to custom designing these energy materials.
That's the goal. To use this fundamental knowledge to engineer truly revolutionary energy storage solutions tailored for specific needs.
It sounds incredibly promising. But realistically, there must be challenges in taking this from computer simulations and lab benches to actual products.
Oh, absolutely. There are always practical hurdles. A big one is simply scaling up production.
Right.
It's one thing to make a few milligrams or grams of a perfect material in a highly controlled lab setting. It's quite another to produce it reliably by the kilogram or even by the ton for industrial use.
The baking one cake versus opening a bakery problem.
Exactly like that. And related to that is cost.
I was going to ask about that. Are these materials expensive to make?
Currently, the starting materials in the synthesis processes, especially those requiring precise temperature and atmosphere control, can be quite costly. Finding more economical ways to produce them at scale is definitely a major challenge for commercial viability.
And maintaining quality when you make large batches.
That's the third piece, ensuring that every batch has the same precise structure, the same sodium content, the same performance that requires very sophisticated process control and quality assurance, which adds complexity and cost.
So scaling, cost, and quality control. Significant challenges.
They are, but they're engineering challenges that are being actively worked on.
Despite those hurdles, the future outlook still sounds pretty bright.
I think so, yes. The fundamental potential of these clathrate materials, especially for batteries, is just too compelling. If these challenges can be overcome,
Then what?
we could see a real revolution in battery technology. Devices that are significantly smaller, lighter, pack more power, and last much, much longer than what we're used to today.
And that impacts everything.
It really does. From consumer electronics to electric vehicles to grid-scale energy storage, the broader implications for our energy systems are huge.
But we're not quite there yet. More work needed.
Definitely. There's still a lot of research and development required to fully understand all the nuances and to unlock the full potential of these type 2 germanium clathrates. We've really just scratched the surface.
Okay, so let's quickly recap the key takeaways from our deep dive today.
Sounds good.
First, We learned what these type 2 germanium clathrates are, these amazing, intricate, cage-like crystal structures that trap guest atoms, in our case, sodium.
Right. Those molecular prisons or maybe honeycombs built atom by atom.
Second, we really dug into why the movement of those sodium atoms is so critical, how they get out of the precursor, how they navigate inside the cages, how neighbors affect them. And all this directly impacts battery performance, like charging speed and lifespan.
Yeah, the social network and travel habits of the atoms are key. And we saw that tiny 5.45% volume change is a huge stability advantage.
And finally, we touched on the powerful tools scientists use, those advanced computer simulations like DFT, the virtual microscope, and EDB, the atomic GPS. These aren't just for observing. They're actively guiding the design of better, more efficient materials for the future.
Exactly. They provide the roadmap for engineering these materials from the atom up.
So a final thought to leave our listeners with.
I think it's just that reminder. It really does all start with understanding atoms, figuring out their social networks and their travel habits at that incredibly tiny scale. Well, that knowledge could quite literally power our future.